So good evening, everyone, and thank you for joining us. My name is Marwa Shafi. I'm an associate professor of electrical engineering at NYU Abu Dhabi, and it's my great pleasure to introduce the speaker of today, Professor Merouane Debbah. So I've known him since 2013 when I was doing my master's in Supélec in France, and I had the opportunity of taking my first wireless communication course with him. So the class was so inspiring that I ended up doing my research career in wireless communication. And I hope that you will feel the same, equally inspired by his talk today. So I will share a bit of his impressive background. So Merouane is currently a full professor at Khalifa University, and he is the founding director of the 6G Research Center. So his research lies at the interface of fundamental mathematics, algorithms, statistics, information and communication theory, with a special focus on random matrix theory and learning algorithms. He's a frequent keynote speaker at international events in the field of telecommunication and AI. In the communication field, he has been at the heart of the development of small cells, which was a technology for 4G, and massive MIMO, which was one of the main technologies of 5G. And he's currently working on large intelligent surfaces, which is one of the emerging technologies of 6G. In the AI field, he is known for his work on large language models, distributed AI, and semantic communications. Since he moved to the UAE a bit more than 3 years ago, he contributed to the development of Noor, which was the largest language model in Arabic upon its release in 2022. He also contributed to the Falcon LLM upon its release in 2023. It was the top-ranked open-source large language model. And more recently, the Falcon Foundation. And we should all know that the UAE or the Falcon model series and the Falcon Foundation have positioned the UAE as the global leader in the generative AI field. And this is thanks to many contributions of the Professor Merouane. So he received multiple prestigious distinctions, prizes, and best paper awards for his contribution to these fields, communication and AI. And he is a fellow of several international organizations. He also has been leading several initiatives, including the IEEE Large Generative AI Models in Telecom. So today, Merouane will share his vision on the future of wireless communication and how the emerging technologies, particularly AI, will contribute to shaping the future of this field. So, Merouane, I will invite you to the stage, and we are all looking forward to your talk.
Thank you for the introduction, Marwa. And it seems like effectively that was more than 10 years ago. I had her in my class, so it makes me a bit old, but this is how life is, I think. So I think let's have fun during 45 minutes here and at least give you a bit of the knowledge that I've been gathering around the topic of course, wireless communication. And so I've been moving from industry and academia for many years, and also working with different, I would say, type of communities, either information theory, signal processing, mathematics, and also engineering, and now, of course, a lot of AI. And of course, a lot of the work that I've been doing was on the fundamental part, but also on the practical part. And I'm going to talk about how I see basically the next years in terms of communication and what are the things that needs to be done. And of course, for people who have no knowledge around that topic, of course, I'll try to be as much as I can in terms of explaining the different ideas and presenting them. So the classical kind of slide is around what we're talking about, wireless communication. One of the big topics is around what we call the G generation. Of course, wireless is not only G. You have, of course, Wi-Fi, typically, which is basically standard around IEEE, 802.x and whatever. But we'll be mostly focusing about things which are on the mobile market, meaning basically you start moving. And this generation, of course, started roughly, if you can say, in the boom of telecommunication around the 1990s. Of course, on the fundamental part, this dates back much longer and further apart. We'll talk about, of course, Shannon. But we're talking here about, I would say, the industrial kind of application. This started in the 1990s when one of the generation that kicked up quite rapidly, which is called 2G. And 2G was basically focused on what we call providing basically mobile for voice, meaning you could move seamlessly and make a call. We had, of course, systems which provided systems on which you could make a call without moving. These are called DECT systems. You have them in your house, you call, but that doesn't provide you seamless mobility. So engineers came up with some great technologies behind to fulfill that requirement. So it's very important to distinguish what we call a generation from the requirement. So you have basically a G, which is a requirement, mobile for voice, and behind that you can have several technologies. One of the most famous technology that you all know is called GSM. And GSM, of course, is the boom of 2G. But if you went to the US, if you went to Japan, you had other types of systems which were implemented to provide basically that KPI. KPI means key performance indicator, which is basically mobility for voice. IS-95, for example, in the US, to be more specific. Around 2000, and it's a generation which goes around 10 years, we'll try to explain why it's every 10 years, because basically there's a whole process when you build basically these systems, which is related to what we call standardization. You can't build on your own a system like that and start selling it, because it means that a lot of people, and there's an ecosystem, which want to connect to that kind of generation, need to build devices. And so they have to agree on what we call the interfaces. The phone makers, for example, you have various phone makers, but also the manufacturers of the infrastructure. You can call them Nokia, Ericsson, and all these guys. And so in general, it takes a bit of time, we'll talk about it, to build a generation. It's not something that you can build like that and a technology that you can sell, because in general, there is a whole ecosystem which plugs in, and people who make computers need to have basically the interface to connect, basically, for example, to a 3G type of connection. So in the case of 2000, we started building what we call 3G, with one of the requirements being mobile for data. And how we did it was basically, of course, the capability for you to download files. And we were selling a lot of what we call dongles. If you remember, you put that dongle and then you were very happy to get those things. And of course, behind that, there were several technologies which fulfilled that requirement. I don't have time to talk about them. But of course, one of the most important one was called CDMA 2000, which is called Code Division Multiple Access, and went further in terms of enhancements around those things. Around 2010, so 10 years later, a whole process, we started, of course, deploying what we call 4G, which provided what we call mobile for internet. Basically, having a wireless ADSL experience with mobility, meaning you move around and basically you feel as if you're at home, but with mobility everywhere by having your internet browsers open. Of course, the fact that we had phones which enabled that kind of visualization of internet was key in the explosion of mobile for internet. You have to know, by the way, that the guys who built 4G, and I was part of that, were so focused about providing mobile for internet that voice did not work well in 4G. And there's also a lot of operators which are deploying 4G for which voice does not work well. Why? Because in 4G, it's voice over IP, okay? So what it means that it's like WhatsApp. It uses the internet to get you basically with the voice. And voice is not a technology, it's an application, okay? And we have a system called voice over LTE, because the technology behind is called LTE. And you have to know that when we sold basically 4G, many people were complaining, because on the phone, whenever they made a call, they had this WhatsApp experience, and a 2G phone was much better than a 4G phone. And so during many years, around 6 years, from 2000 to 2010 to 2016, we had in every phone a system called CS fallback, meaning whenever you made a call, you would go on a 2G, 3G network, and whenever you browsed on the internet, you were on 4G. And you never saw that, because basically we hid that kind of features, and we never told you that we had to go on 2G, 3G whenever you made a call, because people were not satisfied. It took us a couple of years to fix it. AI was part of that, with a system called AI-based voice over LTE. I can spend time explaining that. But I think that's quite important also to understand that when you're so focused on something, then sometimes you forget that at the end, phones are still used to make calls. And so they're not just there to browse. And so that was a big also kind of understanding that we had to make around that. 10 years later, 2020, we started, of course, building basically the infrastructure that provided what we call mobile for things, what we call mobile for IoT. A massive number of devices which are connected, basically sensors, temperature, whatever you want, through a 5G network. Unfortunately, the first deployment of 5G that we made, well, we realized that people are not really making, or we're not making money out of IoT. We don't know how to make money out of things. We know how to make money out of calls. We know how to make money when you browse. But from machines with wit, it's very difficult to make money. And so one of the big things that are deployed today in 5G is what we call the mobile broadband. You're still having basically capacity, basically browsing on 5G, and not what we have built the 5G for, which is basically low latency network for the IoT devices. And that's unfortunate because it's just a question of we are not imaginative enough on understanding how we can make what we call new business cases or use cases of IoT. Everybody has tried to do that. You have to know that a lot of operators were trying to purchase and make money out of localization, meaning whenever you deploy bikes, they put a sensor on a bike, and then being able to track your bike, then you would pay for something. But people were not really willing to pay a lot of money for that. Or if you have a necklace or a ring, we would put a sensor, and wherever it gets lost, you can still find it. That's great. But people are still not willing to pay money out of that. And one of the reasons is that we realize that the connectivity of IoT is not bringing money. It's how you use the data behind, for which you can make money. And so starting next year, we're going to be seeing more and more developments of a lot of, I would say, nice use cases on which we can, of course, exploit the massive amount of IoT devices. We're talking about 1 million objects per kilometer square. You can imagine related to that. And basically, of course, start to find basically use cases around those things. But you have to know that that was a bit of a failure, and 5G is not kicking in right now. We're still selling 5G, and for you, many of you, when we sell you 5G, well, you're not willing to pay a higher subscription because you're not seeing the difference. You're saying, I have a 5G phone and a 4G phone, but it's nearly the same. Why should I pay plus? But because the target was not exactly that, of course, we're providing more data rate. But of course, it's open to all of you guys to start being inventive in how we can make use cases out of connectivity. Connectivity is key here. And of course, connectivity, you're never going to be making people pay with the number of bits which are transmitting because it's usually twits. A machine is on, is off. These are the kind of things. So if you make people pay by the number of bits, that's not going to happen. So what we're working now is another milestone. And the new milestones that we're working is a milestone for 2030, 10 years later. And one of the big things that we're seeing now is a massive number of devices with AI on it. And the question that we're asking ourselves is if we have basically intelligences which are connecting or talking to each other, what is the kind of protocols that we have to build to make these systems work together? We are living in a massive world with massive devices which will have what we call AI enabled in them. This is called edge AI. And the question, of course, that now we're realizing is that in the future, we will have what we call agents, we'll talk about them, which are talking to each other, which are your personalized agents where you're out of the loop and your WhatsApp is discussing with another WhatsApp, which are just basically AIs talking to each other. And the speed at which they're talking, the way they're talking is totally different. So I'll give you a couple of examples related to that. So of course, this has shifted also from a fundamental understanding what we're doing. So of course, the key in telecom was basically due to a model of a guy which is quite known called Shannon. And many of you, I think, know him. And he was working at Bell Labs, which was one of the key, I would say, centers in the 40s. And Shannon came up with a model which is quite known about how you transmit data from one point to the other point without any error, which is related to a notion called capacity, meaning the number of bits per second per hertz that you can transmit with zero error. And this, of course, has shaped all our community during many years. I would say until 10 years ago, everybody was working on, of course, achieving that number of capacity. And of course, the way you achieve it is through a process called coding, okay? Which is, for mathematicians which are in the room, quite nice because you can always prove basically a limit, but you don't have a constructive way of building it. It took us many years to find ways or a constructive way to achieve that capacity. And those are a series of code which were invented by many communities, going from turbo codes to LDPC codes to Polar codes. We were able to achieve that. And that was on the left. And that's exactly the scheme that you see on 1948. I think we clearly closed the picture in terms of how you transmit. Although that system was done on a point-to-point setting, meaning I transmit to you, there is still, of course, some openness in terms of understanding how you do what we call multi-user system, because in a communication, I never talk to one. In general, I talk to many, or many talk to me. So there's various cases, and this goes into what we call network information theory, which is still an open topic. However, what we saw quite recently is that the model does not fit in what we're seeing today. What we're seeing today are devices with a lot of storage capability and a lot of processing capability. And when you have devices which have a lot of processing capability and a lot basically of storage capability, the model changes and the way you communicate also changes. Why that? Well, basically, it means that the more I communicate with you, the more there's a common understanding between both of us. And so the more I communicate with you, the less I need to communicate in the future because you're able to store all the past communication. You start building a model of how we communicate. And we'll talk about that. And it's at the heart of new systems that we're building, which are based on what we call semantic communication, which of course has a huge impact in how you compress, which is the case in your husband and your wife. There's things you don't need to say anymore when you spend so much time talking, because there are things that you can immediately be commonly understood between your partner, wife or husband, because you talked a lot, which is totally different from a version of Shannon where every communication starts as a new communication. Clear for everybody? So that's very important. And so those notions are very important because basically we were able to realize that if we start building models of communication, then we could enhance the way the communication is based, and of course we can improve. And so what we're seeing, of course, is the power of having basically on each device AI running and on which basically we can improve the system with more communications. So the more you communicate, the more you become efficient in how you communicate. So that's very good because that's at the heart of what we call learning. And this is exactly what happened quite recently. Of course, this is possible today because there has been a revolution. So these ideas, by the way, are not new. We knew also by the time of Shannon, and it's called level B communication, by the way, this notion that the more I'll communicate, the more I'll be efficient in how I communicate because I start learning a lot of features in the way I build my system. However, we saw a big transition is many of the ideas which were built since the 48, in fact 56 until now, were already there. But what happened is computing made a big difference. And a lot of the ideas that we had, we can process them thanks to the computing capability that we have. And in fact, you can see that the biggest progress that we've been making these last year, and this is a citation of Richard Sutton, are based on the fact that computing was at the heart of this progress. All the guys who work on machine learning, and I think there's many of you here which are working on that topic, the majority of algorithms date back to the 90s. We all know them. Of course, you can always improve them a bit like this on the left, on the right. Or instead of doing a gradient descent, you're going to do stochastic gradient descent. You're going to do some kind of epsilon, whatever improvement. But basically, the biggest progress that you can feel is computing. And by the way, we'll talk about it in the revolution that I know very well in LLM. Computing is really all you need. You don't need to think hard. You just need to build a transformer and then just pour in more GPUs, and your model is going to be much, much better. Of course, it's an engineering art to build it, but there's not fundamentally like a breakthrough in terms of science. So this notion of computing is all you need seems a bit weird, but I'm going to give you an example if you have no knowledge about AI, which is, I think, very nice because that's exactly the example I usually give for students and kids in terms of understanding how it works. Because it's not magic, it's quite obvious. So here you have two pictures. One on the left is what we call ballistic kick. And the other is Newton, that you all know. So if you're at the age of high school, there's a classical exam that they give you to basically find what is the angle theta you need basically to kick the ball for a given distance d. Okay? So when you're at high school, they give you this famous equation, which is called m times acceleration equal gravity. And then by solving it, you're able to find basically the kinematic of that kick, find the theta based on the distance. So you're able to build basically some kind of model of the system and have some notion of how things work. But in many cases, especially in this communication, we'll talk about it, you can't have access to a model, but you still need to kick the ball. So how would you do it? Well, it's quite easy. You go to what we call the brute force approach. So you just kick the ball like hell. So if you kick the ball like hell, you put in one column angle, the other column distance. Clear for everybody? So distance, angle, and so you kick 1 meter or 2 meter, and you put every time the angle. Quite magic. If you're asked to kick the ball at 60 meters, what you're going to do, you're going to look on the table if 60 meters is there. If it's 60 meters is there, then you can find the angle, and you solve the problem that you had in high school without knowing Newton. This is not new, by the way. It's called data mining. It requires some very fast algorithm to do the search because you're going to do it in a smart manner. You're going to look in a database, and you're not going to do 1 meter or 2 meter because it takes time. So you need to be fast. Where you could talk about a bit of machine learning, but it's nothing else than regression, is if the distance is not there. And if the distance is not there, it seems quite obvious that you're going to do some kind of approximation. You're going to look, I have 55, 65, I need to kick at 60. So in the angle, I'm going to do some kind of approximation, or I'm going to learn how to approximate the function which relates theta to distance. Clear for everybody? And so you're going to do a learning algorithm, and you're going to find it. Magic. With this technique, you're able to replace Newton's equations, you're able to replace Maxwell's equation, you're able to replace many of the fundamental laws. So it seems extremely magic, because a lot of the problems I'll be talking about corresponds exactly to modeling how the system is doing. And by throwing a lot of data and throwing, of course, a lot of compute to do all these calculus that I talked about, it can do it. By the way, this approximation that I talked about finding the relation between x and theta through a function f, where you need to learn the function f, corresponds to projecting that function in a database, in a basis, sorry, not in a database. So if you go back to school, if they ask you to find the function f, well, what you do is say f is very hard to find because it lives in a certain space. What I'll do is basically polynomial expansion of it, okay? So theta is equal to a0 plus a1x plus a2x plus anxn. The size of your polynomial is basically the size of your model. The coefficient of your polynomial is the weights. Learning basically the approximation corresponds to finding a very nice optimization algorithm that we can do for that. And we know how to do it. Unfortunately, we don't do the approximation with the polynomial. We have basically, of course, a neural hardware architecture on which we can project that function and learn it quite fast with some very nice frameworks to do it. And typically, you found a way to do it. So it's very magic because compute is all you need. If I have computing and calculus, I could just throw numbers and can get it. Of course, there's some caveats that we haven't solved for that. But for many cases, it's quite nice. And by the way, this technique that I'm talking about is effectively used today in wireless communication to do what we call beamforming. So in general, when you want to transmit to users, it's very hard to know what kind of precoder, what is the system. So you just launch on some directions for some position. And next guy who's in a given position, you will interpolate to find in which position you can beam towards him, which corresponds to your kick when you send basically the signal towards that destination. It's called AI-based beamforming. 3 caveats with this approach that we all know. The first one, I went quite fast. You learned and you kick the data when it was sunny, and the day you're asked to kick, it's windy. It doesn't work. Because basically, you need a lot of data for when there's a wind of 1 kilometer, 2 kilometer, 5 kilometer, 6 kilometer, 7 kilometer. It's how you can do what we call transfer learning. I learned when it was windy or when it was sunny, and I can still learn on the other side. A bit tricky. Second, I went quite fast and told you, and this is at the heart of these systems when you start building AI, is I told you there was a one-to-one relationship between theta and x, or the distance. In fact, it's wrong. Theta is a function of the distance, but also the initial speed v0. That's why I put the v0. If you go back to school, you need to know the initial speed. And so this guy becomes quite tricky because in many scenarios, you have many columns, but you don't know which columns you need to put. It is as if you were going in a hospital and then the doctor tells you, hey, you're a data scientist, you're very smart. You have temperature, cancer. Clear? Now, I give you the temperature of a new patient. Tell me if he has the cancer. Then you, oh, whoa. I can't do that. Then the question is, which column are you going to put blood pressure? So you put blood pressure, temperature, and finding a relationship is not easy. And so it turns out, although you throw numbers, it's not very evident to know what are the input-output parameters of your black box. And the last one where we're stuck, but again, all these things are not related to effectively machine learning. At least it's related to the way we do it. The last point is whatever you kick on Earth, you learn as much as you can. The day we ask you to build a rocket to go to space, you're stuck. because basically gravity is totally different there. And so we have an issue of generalization, which we all know, okay? And that's not related to the fact that machine learning techniques are not good. It's the way we do it, which is based on this function approximation that I was telling you about. We know typically that if you want to be very smart, then you need basically to be able to extract gravity from your data. And gravity is what we call an invariant, meaning it's invariant by translation, rotation. So you need to use some sophisticated mathematical tools, such as by transformations that you can do. There are things which you cannot change, and those are the things you can learn. But today, these kind of tools, well, the community has not built them yet. And so it's very hard today to be able to go on outside the classical topics that people use, which are the kinds that you know around these things, okay? Now, of course, this is when you start using techniques which are building for learning a function. Now, it turns out that some smart guys in 2017 came up with also a new technique, not to build models which are basically for a single task, but what we call for multitasks. And this is basically an architecture which was built based on transformer, meaning that when you start learning your system with enough data, and for which you train from some given task, they're able also to give you answers for other tasks for which basically you did not train them for. And so this is why basically people are also interested in this architecture that we have built, is what we call these few-shot learning basically capabilities. So it is as if I told you that you learn a machine to be good in addition, you learn a machine to be good in division, but it's able then to know how to be good basically in multiplication, because it's able to find also its way around that. It can't find everything, of course, otherwise we'd have solved all the problems. But basically, we have basically what we call these few-shot learning capabilities. And that's very interesting because a lot of the devices that you build, you don't know what you're going to tackle after. So you have in mind some use cases, but you want a system to be still robust in dealing with new things that you haven't seen on the fly. It will not, of course, solve all of the cases, but already it's a smartness, some intelligence that you brought in, because it's questions, answers, datas, or combination that you have not foreseen. And a lot of people are happy with that because we never trained the system to be good at that, and it turns out to be good at that. Whereas the classical techniques were more based on that. And LLM, or these large language models, based on the fact that, of course, you pour in huge number of data and huge GPU, turn out to be very efficient. And the more you train with no more GPUs and the more you put data, the more they're able, again, to, of course, tackle new tasks you haven't seen. Now, how does it relate all this to communication? Well, the first one is these LLM have become so strong that basically they have become also super compressors. What I mean by that is that crazy, you can have a prompt that generates a text. I think you've been using ChatGPT before. But a text can generate a video, can generate an image. Clear? But then if you want to transmit from one point to the other point, remember what I told you? When we go back to the notion of Shannon, well, if the other guy has the model and learned the same thing as me with his experiences, then why should I send him the video? Because he could reconstruct it. Clear for everybody? So what I'll do if I want to transmit to my neighbor is not anymore take my video, zip it, and then send my zipped video, and then he's going to dezip it. I'm going to do video to text. Clear? A very small representation of the video. Send him the text, or what we call the instruction, and then he's going to generate text to video. So imagine basically a world where we're not transmitting data anymore, but we're just transmitting instructions. Because you can regenerate based on the knowledge that you have, which is similar to mine. So there's two caveats, of course, for doing that. Otherwise, we'd have been deploying it. The first one is it has to go fast. And if you use these image to text, text whatever, it takes a bit of time to do what we call inference. You don't have the text immediately, and especially in image, it takes a bit of time. A video of 1 hour, you can imagine how much time it would take you. So you need to build a system where you have what we call mobile edge generation at the speed of light. We're a bit far from that, but we have to work hard to build the systems where you can regenerate basically anything extremely fast. Second is also something that we discovered is that if you prompt a machine today or an AI with a prompt, it gives you an answer. Clear? If you prompt it 2 hours later, it will give you the same answer, but not the same text. It will not have the same text if you tried it. Try to prompt, ask, and then try to prompt again and ask. You'll see that the text is different. Which means that on the other side, there's never going to be what we call perfect reconstruction. It's not going to be the same. But when we think as how we humans are, we never reconstruct the same. If you ask me a question, I can give you the answer. But I'm incapable to give you the same wording in 2 hours if you ask me the same question. But I'll give you the same answer. Clear for everybody? And so we're trying to build systems which are more and more like humans, where the person on the other side will be able to understand basically the message we sent him, although it's not the same. So you need to define new protocols, which are based basically on what we call semantic communication. And this is coming in right now with all the work that people are doing by providing that latency requirement that I said. Second thing also that is also quite dramatic in terms of changes is that these last years we saw also some changes in the philosophy on how we communicated. And I think this is also very important for the future of communication. And this is related to a topic I've been working a lot, which is called large intelligent surfaces or intelligent environments, which is basically when you go back on the Shannon point of view, what happens is that whenever you make a call to somebody, well, if the communication is not good, what do you do in general? Well, if the communication is not good, well, there's some problem. So what you do, you move. Why you move? You move because you want to change the environment of your communication, because you feel that there's a wall. You're in a position where the environment is not helping you in communicating. Clear for everybody? And so for many years, until 10 years ago, the only way for us to communicate was either to improve the transmitter, making better phones, improving the receiver, making better receivers. But the environment was taken as something for granted. We could not change it because you can't move the wall physically. Clear for everybody? It's not possible. You're not going to destroy the wall. So what you're going to do is move physically to change things. In the last 15 years, the community has come up with something great, which are called basically intelligent surfaces, on which what you could show is that surfaces on the walls have some properties that can be changed digitally, so the reflections are changed. Typically here you have an example. When you send a wave, you can change and configure directly basically the reflection coefficient, so it goes in another direction. So it means that it's not anymore the transmitter that you can change, but the receiver that you can change, but the environment totally that you can change, which is great. It means that the wall here is a helper for your communication. Imagine an intelligent building which starts doing these things. Now, this is one part. We've been working on that, and it works. Of course, there's some caveats related to how you do it, and a lot of people, and I think you saw some talks here of some people showcasing you the power of those large intelligent surfaces. However, what they have not told you is that now we're working on embedding the walls with AI, the environment with AI. And so the environment understands by itself, you don't need to do anything, how the changes should be to improve your communication. And so this is what we call LLM for IoT. You can control the waves, and the waves are learned by the environment. And the more you will be making calls, the more the walls will understand what are the best way to change its texture to improve basically the system to provide you constructive or destructive interference. So in some sense, what I'm telling you, you're making the environment a living entity, which is something that people are not realizing at the moment. It's as if I was walking near the door and I say, hey, door open, it opens. You're talking to the door like an LLM. Clear for everybody? Or you're putting your hand and then this thing, if you get in another context, says, oh, you're putting too much pressure on me, take off your hand. It starts talking to you. You have an environment which starts being intelligent and talking to you. And this, from a telecommunication perspective, is outrageous because it means that the environment starts understanding how to change its properties to do it. Of course, today we're already doing it, you have to know, in some very specific cases where we are deciding and telling to the environment what to do. Okay, we tell, okay, change this coefficient and it does it better in terms of improvement. But once you embed all these systems in that way, you have a drastic way to do. And the third thing also, which is quite important and I want to mention is, of course, something even more important which is coming and for which we need to build infrastructure. And these are what we call telecom AI agents. So What are we talking about? Today, when you have a phone, basically you are, to book a car, which is a very good example, what you do is that you download a certain number of apps, and basically you click on the app, call Karim, and then you put the address and doing these things. But why would you need an app? An app is nonsense, and the apps are going to disappear. Already in the last Mobile World Congress, T-Mobile, Dutch Telecom, was already announcing some free smartphones or free, what they call free smartphones from apps. You just need an interface where you say, I want a car in 5 minutes. Clear? That automatically will go to the marketplace of all the different cars. We'll start booking basically the best car based on the best price, getting basically the car to come, and then you book it. So you just need basically a single line with a prompt on your phone. That's it. Your phone is going to be totally empty because you don't need at all thousands of apps. And even if you wanted to play a game, you would say, generate me the app to play chess. It will be automatically generated, and then with the code and everything. So in some sense, we're going in a place where there's no notion of apps anymore. Apps builders will disappear, and you'll only have agents which know you perfectly, and which then do. But then if you start doing that, it means that you need to create a network that connects my agent, which knows me perfectly, with the agent of the Uber, whom is going to negotiate the car price and things like that. And so, of course, doing that is quite important. But how you do it is still complicated because it means that you are not anymore asking an AI to discuss, but basically to solve, which requires a lot of research at the moment. If you look at how internet has been progressing, the 2000s were great because we went into what we call search engines. Within the 2020, we have the appearance of what we call conversational engines. And now what we're seeing is what we call solver engines. Because at the end, when you ask in ChatGPT, give me the best pizza restaurant in Abu Dhabi, and he gives you, this is not what was your aim. Your aim is, I want to eat the best pizza of Abu Dhabi and have the meal at home. That's what you want. You want to taste it. And so what you want is, once you make the request, he goes and ranks the best pizzas, he looks at the best pizzas, finds the number of the restaurant, makes automatically the call, then the call is done, then the price is given, then your credit card is used to do the purchase, and then you get basically a talabat who brings you things like that. So you need what we call a solver. And in general, we humans are not interested to talk. We're interested basically to solve a lot of issues that we have. At the end, you want to solve things for you. And the question is how now we go in the realm of what I call not LLM, basically conversational agents, but basically solver agents. And so this is some work that the team I have has been doing. This is thanks to Sanson Lassols and Thomas Gaillard. They've been working on that. We've been looking at how to solve some cases where we do a request to the network. Reduce my energy consumption by 50%. And you do it in a language type. And you expect basically the AI to solve all the different types. And here you see how we do it. So you say, charge my car, for example, and with a certain price, and you want to go step by step. And the idea is that you want to give your prompt in a language form. The system is able to model it in mathematical form, and then cut the problem into sub-problems where you have agents which solve it and gives you the solution. Okay? So this is what we've been working in a recent contribution that we did for YUPT, and showcasing you how basically from a request which is made, charge my EV by 7 o'clock, but reduce the cost. It identifies that the request you did goes in a class of functions automatically, okay? Here you have the class of functions. It becomes a linear programming problem. It will put, based on the prompt, the different numbers within the different constraints that you have, okay? And then basically we'll start looking at the problem. You see here, 7 a.m. is there, all the problems that you have. Then it goes automatically to an LLM-based solver, which will start basically solving it based on a certain number of classes. And this is, of course, going to be having a big impact, because when you build basically a network on which humans are discussing, a lot of the things that you're asking are basically to solve some problems that you cannot really express in a mathematical form. So here you have the different steps that we've been building. And of course, this example, I mean, you can download the paper, was done basically for an example of charging, because that was the use case for which we were sponsored at the time we did. But it gives you here how it's done in terms of getting into the classes. By the way, nearly everybody now is working on these solvers, because this is, I would say, the next step for the community in terms of going into converting, I would say, language into basically solvers. And in general, that's the hardest part, by the way, is how basically you are able to express your problem in a mathematical form around that. So here, as you can see, it goes in a knowledge file. And that knowledge file, we have, of course, all the different learning that we did related to all the different classes. Then you get a function call here. And then here you can see you have a bank of solvers corresponding to your different things, and you need to understand how to map them. Of course, you don't have the solutions to all the problems of the world. You have to know that now, of course, a lot of work is being done by the community using game theory. So if there's some game theorist guy here in terms of understanding how these solvers interact together, and LLM, what we call LLM games, and going around. Okay, so now what I'm talking about, where are we? Because I'm giving you a vision, but where are we? Well, a lot of things started in 2023. Okay, and 2023 was a key date. In fact, it was a key date for two things. The first is the big rise around large language models that you all saw, which was fantastic. And second is also the fact that the community gathered and started to understand what is missing today in 5G to build all these IDs that we're talking about in terms of mobile for intelligence. And so there were two key important dates in 2023. First, the ITU, which is the International Telecommunication Union, gathered a lot of stakeholders to start defining what are basically the KPIs that we need in terms of the infrastructure to get that ID that I'm talking about realistic. And second, of course, in Dubai, during more than 1 month, there was an event related to what we call the World Radio Congress, which takes place, in fact, every 4 years, where all the different community gathers. In that case, it was roughly around 150 delegations from 150 countries with more than 1,500 people gathering to predefine basically the kind of bands, frequency on which we're discussing. And of course, we came up with what we call the KPIs. Remember, what is needed to make the systems of working? And today, we have a clear definition that to make the kind of IDs that I'm talking about work, then you need to satisfy all these things that you're seeing on the green over there, which are related to having 1 terabit wireless, to having basically latency of 0.1 millisecond, and you can imagine how hard it is when you have an end-to-end system building on that. You need also a lot of localization mechanism, which are very accurate in terms of positioning objects to do all these IDs that we have. And so we have the KPIs, and people are working on the technologies to do that. I don't have time to talk about all the technologies, but they're not all AI, of course, because we want to build a platform today for that, for making this super computing AI fabric that I'm talking about. But behind, there's a couple of key technologies, if you're interested, around holographic MIMO and other things like that related to that. And we also think that once this is going to be built, it's going to be also the open door for what we call AGI. We think also that a lot of things that are happening today with respect to AI is that a lot of the things that are built around AI is learning from actual data, but they're not interacting with the world. Clear? There's a feeling that all the models that we're doing are not grounded to a reality. And a lot of the features that are built related to what we want is, of course, providing what we call the sensing capabilities of these things to interact. And that's one of the things that we're building now with terahertz bands, things like that, if you saw some talks around 6G. And that, we think, also is the missing block to build basically that grounded reality. Because any LLM or any kind of system that you're building learns a lot on textbooks or videos, okay? But typically, a system will tell you a lot on snow, okay? It can describe snow very nicely, by the way. However, it never felt snow, okay? So there's a bit, and you can see it. Same thing, you have a very good description of pain. You can ask a machine to tell you pain, how pain it is, because it learned pain from all the books, but it never felt pain. And so there is a missing link on this, what we call converging the digital world with the real world that needs to be done. And the sensing capability is part of that, to make that happen. And that is quite near what we could build in 2030 and what a lot of people are expecting related to that. We still don't know if that's the whole way to build these systems, but we know that this is a missing link that we need to solve related to that. Of course, the timeline, I won't talk about it, but for people who are interested on the timeline that is expected to build all these technology, we're talking about a timeline of 2030. Now, I told you in general, it's a long process, unfortunately, because the building of the technology is forecasted by 2026. And in general, it takes you 2-3 years of people sitting on the table, discussing, on voting, on saying we want to implement this. And that's why in general, it takes 10 years before you build these generation. They're not things like you can improve for any system, just like saying, I'm going to build a system. So there's a lot of stakeholders. In general, the timeline is a bit longer than expected because, of course, the whole ecosystem plugs its systems around those things. Now, to make the vision happen for the telecom domain, and especially the examples I gave you, well, we think there's 3 things that need to be done. The first one is a lot of research on building more and more what we call foundational models, these AI, you remember models that we talked about, which are today so huge but cannot run on a device, and for which basically there's a need to be able to find ways to run them at an energy cost which makes sense on even an IoT. Today there's 2 ways of doing it, but I think some smart guys will come up with new ideas. The first one is to take a big model that you have trained, okay, and then basically quantize it. Clear? And make sure that basically, instead of being billions of parameters, well, basically it runs with less parameters with a bit of loss. A lot of people are working on these techniques of quantizing big models and running these models for training and inference at the same time. Second is smarter is to say, I have an architecture, a physical architecture, which requires that my weights can only take, for example, 0 and 1s, for example. Clear? Because basically you're constrained by the resolution of your hardware. And then basically build a model and training architecture which enables you to build a model physically that can only fit into that environment. These are things called binary neural networks and things like that. If you go on that path, then it's much more complicated because all the frameworks that we built on doing gradient descent, things like that, do not work. Because if you want to learn, by the way, learning is optimization. Now, if you want to do optimization where you impose an architecture which is fixed, like 0 and 1, then it becomes combinatorial optimization because you can't do a gradient anymore. You can't do a derivative. And so if you do combinatorial optimization, as you know, the gates are wide open for all the heuristics. It becomes crazy, the number of possibilities for you. People who know the Viterbi algorithm can apply it and going for that. So that's a big chunk on which basically companies like Apple, Qualcomm, all these companies are working intensively because you want a phone for which you can build an AI on it and for which you can run it for many hours. Second, also, we're in the telecommunication domain and you want to build models basically which have multimodality. Because basically the idea is not text. You remember you have videos, you have images, but you have also voice, you have also radio frequencies. And so how do you create a model where you can do, for example, RF-GPT? How you can, from an RF signals, do 3D imaging, for example. It's crazy. But this is not crazy by itself. People who do signal processing know that in the radar community, if you see basically the signals of a radar, you can tell me what kind of airplane has come. Now, the question is, if I input my machine just with the RF, can I see the airplane? Can it generate me the airplane? Can you imagine the potential, meaning that you would ask a machine, where is Merouane walking in the room, in which position he is? And only with the RF sensing that you have, you can tell me where you are. So we have much more modalities in the domain of telecommunication than the actual guys which are doing. This is, of course, a big potential. And the last one, of course, is building the infrastructure to make all these connected. So we started with my group and also colleagues of TII, basically working quite intensively on building the first telecommunication model, text only, called Telecom GPT, which was fine-tuned for the telecom domain. And so this took us a bit of work, but we decided to start, not everything, but we start basically on building a model which has features and it excels in everything which is related to telecom. We don't have the RF, we don't have the images, but we have at least basically a lot of things that we can build on and building that model. It made a headline a couple of weeks ago, in July especially, because it was the first model in the world in telecom GPT, and especially coming from the UAE, that also put a stand, which was much higher for us. You can find all the details on how we built that model step by step in this paper done with me and my colleagues, and I think we're quite proud of. And by the way, we also decided because of that to launch an activity related to IEEE in basically making sure that we have a standardized type of approach for all the community to start building these things. And so we started, of course, to look at two examples in terms of how these telecom GPT could at least not solve all the communication, but improve what we call the productivity of people working in the domain. And so what we started is, of course, scratching data sets, because that's hard. You need to get all the data set that you can imagine in the telecom domain. Develop also benchmarks. So I don't know if you have experience in building LLMs, but if you build an LLM, the first thing that you have to ask yourself is, how can I assess that what I'm going to be doing is good? By the way, that was a very good experience, because when we built 2 years ago, I think he remembers, Noor, which is a model in Arabic, we didn't have a benchmark. So nobody could assess if your model is better than the other, because nobody can tell you what are the features that tells you that an Arabic model is good, because it knows the Quran, so you need to define basically what are the key questions that if your model succeeds, you're good at. And in many domains, you have to know that the evaluation system is broken, because besides the English domain, in all other domains, there's no consensus in the community in saying, it's like exams. You say at the age of 18, how can I assess that you're smart? Well, basically, we spent many years in defining that the age of 18, if you know this, then that's basically what we think makes smartness, and for which we all agree that the best who does that is the smartest guy. And so in each discipline, you need to do that, and so we needed also to spend time in defining those benchmarks, and also doing the training. So 3 things. First, taking all this, here, as you can see, the sources. We scrapped everything which was open source, because we can't get access to what companies are doing, and then you can fine tune it. So you take everything related to documents in 3GPP, IEEE, and other things like that. Then you do the extraction and pre-processing, and then you go into what we call the specific task. The description of the different, I would say, blocks are here related to the telecom GPT in terms of how we trained the system to build an LLM tailored to this telecom GPT. And here you have also the kind of percentages that we took, because this is also important. Depending on the size of the data that you take, how much you put more than other documents, you have different features which appear, and they're all detailed in the paper and how we're doing it. And also the number of GPUs that was required to develop the telecom GPT, and all these aspects that you can find also in the paper related to that. And quite surprisingly, of course, I mean, it's not surprisingly, but of course, by tailoring it exactly into the telecom domain, of course, we got great scores, and that's one of the reasons people were extremely happy, is that, of course, we were beating state-of-the-art models like Llama that you know, Mistral that you know also, and GPT-4 also that you know. So that was very good for us. Of course, in those questions that we're asking related to the model. So of course, you're asking me, but what is he talking about? So let's take a couple of examples. I'm not going to compare it with other LLMs, but just to give you that the benchmark that we had was quite up in terms of what we do. But typically what we're talking about is exactly this. You have an interface, and these are the things. You ask a prompt. So here you have a prompt which says, what does basically IM stand for, and why is it considered basically desirable for cancellation in communication systems? And then the system gives you an answer which is quite accurate related to your domain. Same thing below, index modulation, and it gives you the answer related to that. This is basically what we call one task that we want from these models, is to be able to understand telecom standard, research papers, patents, and things like that. So you don't need to spend time in all these things. Second is, you want basically to have some kind here of explaining techniques, identify problems, propose solution in telecom. And so you ask the machine, describe the process of providing here basically authorization to a mobile, blah, blah, blah. And you have the text basically which is there. Another thing, you want to go in a process. So you have your technician who wants in the domain to solve a problem and doesn't know what is number 1, number 2, number 3. I need to plug cable red and then cable green, things like that. So here you say, initiate event-based charging with decentralized and a centralized unit determination, and then basically tells you 1, request, 2, top, 3, and he gives you the different things. Third thing also, which people like, is basically analyze code functionality and operation logic of telecom features. So you tell to the guy, oh, I have a bug, analyze the script and tell me. And it's a very script which is very telecom oriented. And of course, this was done by training on all the different codes that we have. And as you can see here, it tells you the scripts describe a function, BCC, and you have all the details, which are very accurate. Of course, if you can run it on other models, you won't get the answers exactly like this. And this is how we benchmark, of course, our system. Same thing, you want to create some code, and especially for students who are doing their internships or projects, and in which they don't want to generate MATLAB code related to some exercise that they have in building an OFDM system or whatever. But here, typically, that's what you do. You ask basically to generate a script or a function of a given task or functionality in telecom. I want you to generate a MIMO system, blah, 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 whatever, things like that. It generates you the code in C, MATLAB, whatever, because also we trained it on all those systems so that you can generate. So that's very quite magic, because again, things. And again, for people who do research, you don't want to write all the equations. So you tell him here, okay, I wrote this paper, but fill the gaps based on your understanding. Okay, so here you see there's masks. You don't fill it, and you ask him, okay, I wrote this paper, but I don't have time to do all the things. In general reports, documents, which require a lot of heavy, basically, completion, things like that. And the system automatically, of course, completes and provides you here for the first mask, it's y equal hx plus n. When you have defined what we call an autocorrelation, he knows it exactly and provides you with the autocorrelation function that you have. You ask what is absolutely summable, you don't even write it, and it understands basically the paper, and especially those papers which are very specific to our domain. So there's a lot, of course, more things that you can do. I didn't show all the examples, but this is what I call the Telecom GPT V0, meaning just the initial stuff of, based on the knowledge that you have as an operator, then basically when you go in a company, you don't need to ask anybody, oh, well, how does it work? You just write and then boom, all the knowledge based on the legacy of that experience that you have, and you can build it. So quite remarkable in how you do it. Now, of course, the second step, I'll finish with a couple of 2 or 3 slides because I think it's time. I didn't check my time. Usually I talk, yeah, 7, okay, good. Is of course, I told you this willingness to add multimodality, because that's what we're doing now, okay? Multimodality is at the heart of how you build systems. You're not based on text only. Telecom is not text, it's bits, it's RF, it's all those signals that you need to embed and then basically learn your system. And the third one, of course, and so, by the way, in this thing, we have a nice paper that I strongly encourage you to read. It's on arXiv about this RF GPT ID, about how you convert RF signals into basically 3D imaging and imaging, and in which we start working on generative AI for RF sensing in IoT system done by my colleagues here, and which provides that. And of course, the last one is so I won't talk about the RF GPT, but here you have exactly how we do it. When you need a lot of data, you need a lot of RF signals. If you don't have enough RF signals, then you need to go into basically synthetic data, because again, you can't measure all the data that you can have anywhere. So in general, you have companies which are very good in that, in providing you synthetic data where they solve Maxwell equations, stuff like that, for your environment, so you can get these RF points in different positions and for which you can go. And this is the kind of work that we did with the signal to image and image to signal, just to replicate what I'm talking here about in terms of what you're doing. Of course, the last one, which is a bit more complicated, on which we're working at the moment, is of course building the architecture for those agents, you remember, to start interacting and be able to negotiate and be able, of course, to solve some problem. Because these agents at one moment are given a task and then they have to work cooperatively to do that. We tried it for a very simple example, but we have no proof at the moment on requesting basically the system by itself, where you had a base station and 2 mobiles, where we asked the system, okay, I want you to reduce the energy consumption of my devices while keeping the rate at that level, and let the system run. So you don't optimize it, you don't have a model, and you run it. And in fact, what you can show is that each iteration, basically the system tries to find a solution. So here again, there's no proof, because this is, I think, what needs now to be done, is understanding if the system will always converge for any problem that you give, which is not the case, of course. Some problems are not solvable, what kind of solution it will give. But for some many examples, it turns out that you can let these agents run to start interacting to solve your problem and go in. Okay, I think I'm going to stop here and answer your question, and I hope it was quite interesting on this kind of futuristic look of the telecommunication domain in the next years. Yeah.